In the last lesson, we discussed what is a linear programming problem and the components of a linear programming problem. Those components are objective function, problem constraints, and non-negativity constraints. By this lesson, we will see how to formulate linear programming problems. Let us take one example. A firm manufactures 3 products A, B, and C. The profits from A, B, and C are $6, $4, and $8 respectively. The firm has 2 machines X and Y. One unit of product A needs 8 minutes of processing on machine X and 4 minutes on machine Y. One unit of product B needs 6 and 4 minutes of processing on machines X and Y respectively. For product C, required machining times on X and Y are 10 and 8 minutes respectively. Available numbers of working hours for machines X and Y are 10 and 12 hours respectively. We are required to formulate this as a linear programming problem to maximize the profit. If you are a beginner, it is always easy if you summarize the information given in the question into a table like this. Then you will not miss anything and it will be easy to develop the model. Look at this table. All the information in the problem are there. The most important thing of formulating a problem is the identification of correct decision variables. Once you do it, the rest of the formulation is easy. Now for this problem, we need to decide how many units from each product should be produced to get the maximum profit. Therefore, we need 3 decision variables. Let us define the decision variables as x1, x2, and x3, which are the number of units to be produced from each product. Now we can easily write the objective function. We know the profits from 1 unit of each product and therefore the total profit from x1 of A, x2 of B, and x3 of C are 6x1 plus 4x2 plus 8x3. We will denote this by z and we need to then maximize z. Therefore the objective function is maximize z equals 6x1 plus 4x2 plus 8x3. Then let us formulate the constraints. The table says for 1 unit of A, 8 minutes of processing on machine X is needed. Therefore, for x1 units of A, 8 by 1 minutes of processing time on machine X is needed. Similarly, 6x2 and 10x3 minute of processing time on machine X is needed for the products B and C respectively. Therefore, the total required processing hours on machine X is 8x1 plus 6x2 plus 10x3. However, the total available number of machine hours for machine X is 10 hours. Since the processing hours are given in minutes, let us convert this available number of hours also into minutes. So, it is 600 minutes. Now, the total requirement cannot exceed the total availability. Therefore, 8x1 plus 6x2 plus 10x3 should be less than or equal to 600. That is our first constraint. Similarly, considering machine Y, we can write another constraint. That is 4x1 plus 4x2 plus 8x3 is less than or equal to 720. So, the 2 constraints are completed. Now, the complete linear programming problem is like this. We have objective function, 2 problem constraints and non-negativity constraints. Let us take another example. This is very similar to the first one, but there is a different statement that minimum demand for chairs is 20. Let us see how to write it. Let us take x1 and x2 are 2 decision variable where x1 is the number of tables and x2 is the number of chairs to be produced. So, minimum demand for chairs is 20 means minimum 20 chairs must be manufactured. That means x2 must be greater than or equal to 20. Other constraints you can write in similar way as in the first example. So, this is the answer. Let us see another example. This is a bit different example. Some item has to be transported from 3 factories to 4 sites. We need to find how many units should be transported from each factory to each site in order to minimize the total transportation cost. So, for this problem we need 12 decision variables as listed here. For example, x1 is the number of units sent from A to D and x2 is the number of units sent from A to E and so on. Look at the table. The table gives the transportation cost for sending 1 unit of the item from a factory to site. For example, for sending 1 unit from A to D, the cost is 10. Therefore, for sending x1 units from A to D, the cost will be 10x1. Similarly, we can find all transportation costs with our decision variables. Now, if you take the sum, that is the total transportation cost and we need to minimize it. Therefore, that is our objective function. Now, let us formulate the constraints. If I take the expression x1 plus x2 plus x3 plus x4, what is the meaning of it? It is the total number of items sent from factory A. But we know that the capacity of factory A is 20. Therefore, the total number of units sent from factory A cannot exceed 20. That means x1 plus x2 plus x3 plus x4 should be less than or equal 20. That is one constraint. Similarly, we can write the constraints for the other 2 factories as well. Altogether, we have 3 constraints for factory capacities. Now, consider the expression x1 plus x5 plus x9. This is the total number of units received by site D. The requirement of site D is given as 10. Therefore, the site D should receive minimum of 10 units. That means x1 plus x5 plus x9 must be greater than or equal to 10. That is one constraint. We can write another 3 constraints for the other 3 sites also as listed here. Finally, the full formulation of the problem can be written like this. Hope you have got some idea about how to formulate linear programming problems, and in the next session we will see how to solve linear programming problems.